This paper is about strengthening neighbourhood substitution in binary CSPs. First of all, I'll introduce different domain reduction operations. In this brief outline, I'll give an example and then talk about complexity. So the classic domain reduction operations in CSPs are above all arc consistency, but also another classic operation is called neighbourhood substitutability. Now, in this paper, we've introduced new domain reduction operations which generalize substitutability. So for a snake substitutability, a value b in a domain is snake substitutable by another value a in the same domain if every value consistent with b is neighbourhood substitutable by some value consistent with a. So this is a kind of next level neighbourhood substitutability. An orthogonal operation is conditional neighbourhood substitutability. Here, b can be replaced by a value, but this value may depend on the value assigned to some other variable. And then there's a third operation which is more complicated and in fact subsumes both of these two operations. Just to give you a quick example of what we can achieve with, for example, snake substitution, if we look at the classic problem of line drawing labeling, we want to assign a semantic label to each line in a line drawing such as this drawing. Because of ambiguity between whether this is actually one object or different objects which aren't actually touching each other, the vertical lines are very often ambiguous. So we in fact have an exponential number of labellings of this drawing. But if we apply arc consistency and snake substitutability, then the number of labellings is reduced to 1 because each domain becomes a singleton. So in particular applications, these new operations, such as snake substitution, can be very effective. So what about the complexity? Now, arc consistency has a complexity of ed squared, where e is the number of constraints and d the maximum domain size. Neighbourhood substitutability has a complexity which is ed cubed, so as a factor of d more than arc consistency. What's interesting in these new operations, snake substitution and conditional neighbourhood substitution, is that they both subsume neighbourhood substitution, but they have the same complexity. So we're getting more for the same price. Okay. So now I'll talk about these operations, but in more detail. So I think that most people watching this video will know what a CSP is. Here we're going to restrict ourselves to binary CSPs, and we assume that there is a relation, a constraint between each pair of variables, which may be a trivial constraint, but for notational convenience, we assume there's always a constraint between variables xi and xj. Here is an example of an instance, a CSP instance, a binary CSP instance, with constraints such as less than equal to or different. These are arithmetical constraints and the domains are integers. Now, traditionally, if we apply the traditional operations of arc consistency and neighbourhood substitution, for example, in this instance, we can't reduce the domains. No element is eliminated. We will see that we can, with our new operations, we can perform eliminations. So as I said, our new operations will be generalizations of neighbourhood substitution. So just to recall neighbourhood substitution, a value b can be replaced by a, is neighbourhood substitutable by a in a domain of variable xi, if for each other variable xj, for each value c which can be assigned to this variable, if b is consistent with c, then so is a. Clearly, if we have b in a solution, we can replace it by a. And this is a classical operation which has been known for a long time and is known as neighbourhood substitution. So we're asking, can we do better for the same price? Now, snake substitution is just looking at sort of the next level, adding an extra variable. For example, if between variables xi and xk you have an equality constraint, then neighbourhood substitution could eliminate no value. But snake substitution may be able to eliminate values. So b is snake substitutable by a if for all neighbouring variables, if b is consistent with a value d, then a is consistent with a value e in the same domain, such that e is almost neighbourhood substitutable for d. In other words, it can replace d in all constraints except possibly xi, xk. So this is a slight generalization of neighbourhood substitution. Now, just to see the power of this new operation, snake substitution, this is a very simple instance where we have 4 variables with Boolean domains and we have 4 binary constraints. Now, neighbourhood substitution and arc consistency can't delete any values. And what blocks neighbourhood substitution is the equality constraints, x1 equals x2, for example. But snake substitution can allow us to eliminate all the values 0 from all domains, reducing all domains to singletons in this particular example. So without giving the details, it's just to show that snake substitution is strictly stronger than neighbourhood substitution. Now, generalizing neighbourhood substitution in an orthogonal way, we can get conditional neighbourhood substitution. So now we condition the substitution of b by a by an assignment to another variable xj. In other words, we're replacing b by some value a, where a may be a function of a value c we assign to xj. So this is a strict generalization of neighbourhood substitution, because if we have a constant, then this is exactly neighbourhood substitution. But if a is a different value for each value of c assigned to xj, then we have a new value elimination rule. So here's another example. Traditionally, neighbourhood substitution works well when you have constraints such as greater than equal to, but works badly if you have equality or disequality constraints. Now here we have a very simple example, a free variable CSP instance, and we have these disequality constraints. But by conditioning on the variable x1, in some sense, these constraints are subtracted out, and we're just left with the greater than equal to constraint. So that allows us to eliminate values such as a 0 for x2 or 2 for x3. Now, I won't go into the details, but we're interested in merging these two operations, which seem to be orthogonal. Can we find an operation which generalizes both? Yes, indeed we can. And I call this snake condition snake substitution because there in fact are 2 snakes. Very briefly, we can replace the value b if there is some other conditioning variable xj, such that if a value c is compatible with b, then there is another value g which is compatible with value a, which is going to replace b, and in all other variables g can replace c in a neighbourhood substitution way. And on the right hand side, if b is compatible with some value d for some other variable xk, then this replacement value a is compatible with some value e, which could replace d in all other relations. So going back to our original binary CSP example, where we have a combination of disequality and inequality constraints, here arc consistency, neighbourhood substitution, and even snake substitution and conditional neighbourhood substitution eliminate no values. But by applying a very strong new rule, snake condition, snake substitution, we in fact, little by little, we can eliminate all values apart from one. So we can get down to singletons. Each domain becomes a singleton. I will skip the details. It's not very interesting, but what is interesting is that we can do this even on a problem with many difficult constraints, such as the disequality constraint. Now, to look at a more concrete example, we're going to look at line drawing labeling. Now, I've chosen to study this problem because I don't propose conditional neighbourhood substitution, snake substitution, etc. as general purpose operations to be applied in a solver as we would for arc consistency or possibly neighbourhood substitution. I think we should look at particular applications where these operations might be useful. If the application domain is such that these operations can be do perform lots of eliminations, then we can apply it. So let's look at this particular application domain of line drawing labeling. So this is a traditional problem in artificial intelligence. We have a line drawing of a polyhedra. We have labels, convex, concave, or a depth discontinuity, which is represented by an arrow. Since the arrow can be in both directions, that gives us 4 different labels for each line. And the aim is to label each line in the drawing. And this gives us some information about the 3D shape of the object. Just to recall what this traditional approach, we restrict the kind of objects we can have, and for example to trihedral vertices, this gives us only 6 types of vertices. We then consider viewing these vertices from all possible viewpoints, and we write down a catalogue of labelled junctions. So each vertex will be visible in the drawing as, for example, an L junction, a Y junction, or another kind of junction. And this slide represents all the possible labellings. You have to add reflections and rotations of all these labellings, but that still gives you a very small number. For example, the Y junction has in total, with rotational symmetry, has 5 labellings out of a possible 256. So these are very strong constraints. However, they're not strong enough to give you a unique labelling for each drawing. Here is an example of an ambiguous drawing. For example, the line AB could be a depth discontinuity. In other words, it's separating 2 different objects, or it could be a concave edge. In other words, there is just one object there. And since this is the case in many of the lines in the drawing, you end up with an exponential number of labellings. Now, if we apply arc consistency and snake substitution, we in fact reduce all domains to singletons. So we have just one interpretation of this drawing. Another drawing, very similar type of ambiguity. The lines ABC could be a depth discontinuity or a concave edges. And again, by applying arc consistency and snake substitution, we managed to reduce all domains to singletons. Okay, so we've seen that in certain applications these rules can be useful. So what is the complexity of already testing these rules? Now we know that arc consistency can be tested in order ED squared time, where E is the number of constraints and D the maximum domain size, and that neighbourhood substitution is ED cubed. It turns out that these new operations can all be tested in the same time complexity as neighbourhood substitution. Now this is perhaps a bit surprising because, for example, if you recall the diagram illustrating snake substitution, we had a total of 5 variables and 8 values. So instead of a d to the power 8 complexity, using a naive algorithm, we've actually reduced it to ED cubed. We're actually interested in applying these rules until convergence, and using the traditional data structures, we can actually find very efficient algorithms in the same way as we've done in the past for R consistency and neighbourhood substitution. So for snake substitution and conditional neighbourhood substitution, we have exactly the same complexity, ED cubed, as for neighbourhood substitution. Unfortunately, for the snake snake substitution, I didn't manage to find an ED cubed algorithm. Anyway, we still have these stronger operations, strictly stronger operations of neighbourhood substitution, which can be applied in the same asymptotic time complexity. Now, looking at some other aspects, we know, for example, that R consistency, it doesn't matter which eliminations we do in which order. There is a unique fixed point. Okay, for neighbourhood substitution, we almost have the same property. The fixed point is not unique, but it's unique modulo isomorphism. In other words, you end up with the same size of problem, the same number of eliminations, whichever order you perform the eliminations in. Now, for these new operations, there is not a unique fixed point, which is not surprising, and furthermore, maximising the number of eliminations is actually NP hard. So I show this by reduction from set cover or from max2 set. I'm not going to give you these proofs, but just to give you a taste of these reductions, this is just one little gadget in the reduction from max2 sat to the problem of maximising the number of eliminations using snake substitution. This is a gadget for negating a variable. There are other gadgets for creating clauses or multiple copies of variables. Anyway, these negative results, NP hardness results, are not too important in the sense that we still apply these operations and we'll still get at least as many eliminations as neighbourhood substitution and some extra ones. We don't really care if we get the maximum number of eliminations. It's still not bad. We're not going to waste our time trying to optimize the number of eliminations. Okay, another aspect is these operations preserve satisfiability. In other words, they preserve at least one solution, but they do not preserve all solutions. That's the same property as neighbourhood substitution and is different, obviously, to R consistency, which preserves all solutions. Now, we might actually be interested in recovering all solutions after having eliminated values, finding the solutions to the reduced problems. We might actually be interested in recovering all solutions. Now, for the conditional neighbourhood substitution, this can actually be done fairly efficiently, at least with polynomial delay. This is similar to what happens with neighbourhood substitution. Unfortunately, for snake substitution, then finding two solutions is actually NP hard. So if you really want to recover all solutions, you should not be using snake substitution. Okay, so just to finish with some open questions. One obvious open question is, are there generalizations to non-binary CSPs and or to valued CSPs? Now, it turns out for snake substitution, we've already considered the valued CSP case, a paper 2 years ago at CP. We hadn't optimized our algorithms, and it turned out that we found very few eliminations. But nevertheless, from a theoretical point of view, we have managed to generalize snake substitution to valued CSP. But the other operations have not been generalized to valued CSPs. Another question is, are there other interesting reduction operations, such as, for example, variable elimination rather than value elimination? So there in a separate work, we studied several rules and produced new elimination rules which eliminate a variable without introducing new constraints. And I'm sure there are other reduction operations as well. So what we've achieved with these new operations I presented here are new operations which are strictly stronger than existing operations which have the same cost. So the question is, can we do the same in, for example, var elimination, clause learning, or other reduction operations? Okay, that's it.